The world is constantly changing. Technology continues to develop, especially medical technology. Researchers are constantly innovating to ensure the highest quality of health for humans. Among recent technologies, CT scan has transformed into a very useful imaging modality. Images produced by CT are able to provide an accurate detailed look at the patient's organs in a short time, supporting accurate diagnosis. Image quality is a vital aspect
The world is
that
constantly
must be
changing.
achieved in CT examinations.
Technology continues to develop,
especially medical technology. Researchers are constantly innovating to ensure the highest quality of health for humans. Among recent
research on CT scans continues to grow rapidly. Researchers continuously innovate to give their best contribution to society. All efforts are made to improve the effectiveness of the health services. One of the results of this innovative research is IndoQCT.
Quality is a vital aspect
The world is
that
constantly
must be
changing.
achieved in CT
IndoQCT is a
examinations.
software to automatically evaluate the quality of CT image. IndoQCT can be downloaded on the website www.indocct.com. IndoQCT is able to measure various image parameters from a variety of phantoms available on the market. Measurements with IndoQCT are carried out quickly and accurately. With only a click, the calculation is carried out automatically without much intervention from the user. IndoQCT has three main objectives. First, it's a tool for medical physicists to effectively and quickly accomplish their task in routine quality control of CT. Second, it's a scientific tool for CT scan research. And third, IndoQCT is a tool for educational purposes, especially education regarding the quality of CT images. Unlike previously available software which were limited to certain parameters and phantoms, IndoQCT is capable of measuring various parameters from a variety of available phantoms, such as the AAPM CT Performance Phantom, the ACR CT Accreditation Phantom, the CAPFAN Phantom, the GE CTQF Phantom, the Canon TOS Phantom, the Philips CTQF Phantom, the Siemens CT Phantom, the Newsoft CT Phantom, and the Anthropomorphic Phantom. IndoQCT can also generate synthetic images using a computational approach called the computational phantom, which is useful for educational purposes. The main capabilities of IndoQCT are to measure CT number, noise, spatial resolution, slice thickness, low contrast detectability,
alignment, gantry tilt, distance, and distance between slices. IndoQCT is also reliable in measuring image quality metrics directly from patient images. It's advantageous for simplifying and increasing the objectivity of the dose optimization process. IndoQCT is also equipped with several additional features, including texture analysis, some noise reduction, several windowing options, including multiple windows blending in the form of red, green, blue images. And image reformatting on sagittal, coronal, oblique, and irregular planes. IndoQCT will be able to connect the picture archiving and communication systems to facilitate user in collecting images directly from DICOM servers. It doesn't stop there. With IndoQCT, you can store, measure data to an integrated database. This storage has been facilitated with an export tool to save data in Microsoft Excel document format. IndoQCT provides convenience in the aspect of efficiency, measurement objectivity, universality, and portability. Many international publications have been produced using this software. Research opportunities with IndoQCT are ongoing so that the number of research projects using IndoQCT will continue to rise. The world is constantly changing. Technology continues to develop, especially medical technology. Researchers are constantly innovating to ensure the highest quality of health for humans. Among recent technologies, CT scan has transformed into a very useful imaging modality. Images produced by CT are able to provide an accurate detailed look at the patient's organs in a short time, supporting accurate diagnosis. Image quality is a vital aspect that must be achieved in CT examinations.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, all participants. Thank you for being here. We will continue our online summer course in Medical Physics 2025, IndoQCT for CT image quality measurement. And today we will discuss the easier topic compared to yesterday. We will discuss about the slice thickness, slice spacing, each measurement in morning session. And for afternoon session, we will discuss the advanced image quality measurement in measurement from patient image and its measurement in the afternoon session. And for all participants, before we start our lecture, I want to remind all of you to fill the attendance link that will be sent by the committee in the chat Zoom. And since has come to the sixth day, please prepare yourself to do the elimination test or the evaluation test to get the certificate of attendance, since you must get score above 60 points if you want to get the certificate of attendance. Okay, now I want to greet our speakers today. Good morning, Dr. Hoirul Anam.
Morning.
Okay, you have 70 minutes to deliver your lecture, and without any further ado, please come, Dr.
Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. And now we are in the sixth day of our summer meeting this year. And in this morning, we will discuss regarding slice thickness and slice spacing and its measurement using IndoQCT. And I think this topic is easier compared to the last day regarding detectability index. Yeah. Okay, and we will continue. Okay, our table of contents today is the introduction, and then we move to the discuss slice thickness on the various fandom such as CAT fandom, AAPM fandom, SCR fandom, GE, Siemens, and other fandoms. And then we move to discuss distance between slices. I think this parameter is a relatively new parameter, and in the quality control program, this parameter is not measured. And after that, we will discuss on the slice profile quality index or SPQI. I think this parameter also not to be measured in the standard quality control, but it is very nice to know about the SPQI. And the last will be conclusion. Okay, now we will discuss the introduction about the slice thickness parameters in CT scan. Okay, because the CT produce the axial image, so the slice thickness is very important parameters. And the slice thickness is the main parameters affecting other parameters such as the spatial resolution, noise, and also the partial volume artifact. It comes from the slice thickness parameters. Other than slice thickness, we have also the slice spacing parameters. But this parameters is relatively new and never been discussed, never been measured in the standard quality control. And today's material will discuss also about the slice spacing. And by using the IndoQCT, we can measure the slice spacing automatically by using available fandom such as the APM or OCR fandom. Okay. The slice thickness in the first beginning of the city, it means using the slice city. The slice thickness is decided by the collimator. Okay, but for the multi-slice city or MSCT or MDCT, multi-detector array city, the slice thickness is not governed by the beam collimation, but it is governed by the software. So even the collimation is same, we can set the different slice thickness as our desire. This is for multi-slice city. But for the single slice city, the slice thickness is relatively easy to understand because it it is governed only by the beam collimation. This is the beam collimation, and we have the slice thickness. It is for the MDCT or MSCT, multi-slice city. It is selected by the software and set by the user. And now the slice thickness becomes smaller and smaller. In the first beginning of the city, the slice thickness is around, we can see here, more than 10 millimeters. And now the slice thickness, it can be reduced to lower than 1 millimeters or sub-millimeter. So by using the very very thin slice thickness, we have the isotropic images in the city, meaning that the size in the z-axis is similar to the size in the x and y axis. It is now in the modern CT scanner, but in the previous one, the z-axis is relatively longer and larger compared to the x and y axis. Okay. Yeah, as I mentioned before, the slice thickness will affect to the spatial resolution in the cross-plane image, and it impacts to the accuracy of determination of the size of the organ. In the radiotherapy, it is very important to use the very thin slice thickness because the definition of the organ will be more accurate. This is the example of the image in the maybe in the sagittal or coronal planes. By using smaller slice thickness, the spatial resolution is better. But if we use the relatively larger slice thickness, the spatial resolution is worse. We can see here. By using the very small slice thickness, the detail of the bone is very easy to be seen. It is in contrary with the relatively thicker slice thickness. This is another example, study done by the group of Professor Boon from AAPM. They assess the accuracy in the volume for different slice thickness. And they found the result like this. We can see here, if the slice thickness is becoming smaller, so the accuracy is better compared to the relatively wide slice thickness. We can see here. This one is for the 5 millimeters slice thickness. And this one is for 0.6 millimeter of the slice thickness. We can see here that the percent error is become less, meaning that the accuracy of the volume definition is better. It is another result, and this result is similar to the previous one. This is another example of the stand. We can see here the A and B. The A is the image is from the newer CT scanner, and the B image is from the previous one. And we can see here that using the relatively new CT scanner, we can have the very good spatial resolution because using the very small slice thickness. Okay, and as I already mentioned, the slice thickness also affect the other parameters such as the noise and other parameters. If we use the smaller slice thickness, meaning that the photon comes to the detector will be lower. So the quantum noise will be higher. We can see here from the images, if we use the smaller slice thickness, the image will be noisy. And if we want to reduce the noise with the smaller slice thickness, we should increase the tube current. And it leads to the higher dose received by the patient. Okay, so in the clinical setting, we should optimize the use of the slice thickness based on the clinical purposes, not too thick or not too thin. Because if the slice is too thick, the small object will be less visible. The spatial resolution is not good. But if you use the too thin slice thickness, the image will be very noisy. So it is very important to optimize the use of the slice thickness depend on the specific clinical purposes. Okay, and the slice thickness we use in the clinical setting should be tested in the regular quality control, so that the set slice thickness is similar to the actual slice thickness. This is the IEA standard for the slice thickness. The slice thickness should be less than 0.5 millimeter. The difference between the actual and the set slice thickness. And for the larger slice thickness, the standard is different. So in our regulation in several countries, maybe the standard is different. In Indonesia, we have the standard from the Bapeten. And the standard from the Bapeten different from the standard from the IAEA. Okay, and now we move to how to measure the slice thickness. Of course, if we want to measure the slice thickness, we should have the phantom dedicated for measuring the slice thickness. There are many phantom, such as the APM, OCR, CAT fan, and they have the different design for the measuring the slice thickness. This is the example, the design from the APM, and this one design from the SCR, and this one design from the CAT fan. So basically, they employ the using the line or ram with the specific angle. For example, for the APM, they use with the angle of 45 degree, and for CAT fan they use around 23 degree. And RCR, by using the hole, and this hole will be filled with the wire. So by using the RCR, it is very easy to measure slice distance by counting, by counting this wire. And if we want to measure the manual one using the AFPM, we can use the caliper, electronic caliper. And for the RCR, we just count the number of the wire. Okay, and now we will delve the design of the each phantom for measuring the slice thickness. Okay, and this one is the object for measuring the slice thickness for 3 phantoms. Okay, now we will discuss the design from the cat phantom. So, and this one is the module for measuring the slice thickness, module number CTP401, this one. And this is the RAM, this is the wire with the angle, shallow angle around 23 degree. So if we scan this module, we will have the axial image, and we have this line, and the length of this line depend on the slice thickness. If we scan with the larger slice thickness, this line will be longer. And if we scan with smaller slice thickness, the length of this line will be shorter. And then because the angle is 23 degree, and then after we measuring the length of this line, and then we multiply with the tangen 23 degree, and we will have the slice thickness from the cat phantom. So this one, the line with the angle of 23, and if we scan with the slice thickness of Z, so we will have the line with the length like this, and the pixel value will be average from the partial volume effect. So if we scan with the smaller slice thickness, the pixel value will be higher. And if we scan with the larger slice thickness, because there are so many water with the 0 pixel values, so the pixel value will be smaller. But the larger of the length is linearly depend on the slice thickness. So we can measure the length of this line to deciding the slice thickness, slice thickness, and then we multiply with the tangent of 23 degree. Okay, so the slice thickness is the full width of half maximum or length of this line multiply with the tangent 23 degree. It's very easy to measure the slice thickness using the cat phantom. Okay, and in this example, we can not only measure directly the length of the line, and we can use the profile. This is the example. So we will have these values. For example, in this position, we will have the profile, and then we can create the curve of the profile, and we decide the maximum values, and then we can measure the half maximum. We can decide half maximum, and then we can measure the FWSM, full width at half maximum. So if we multiply the full width at half maximum with the tangent of 23, so we will get the slice thickness using the cat phantom. And this is the automatic method for measuring the slice thickness, and in our team have published in the Biomedical Physics and Engineering Express. This is the automatic method. The first one we detect the phantom, and then we have many steps. After that, we can detect the line for measuring slice thickness, and then we can detect the angle of the line by using the half transformation, and then we can draw the line across the line, and we will have this one, the profile. And then we can automatically measure the full width at half maximum, and we multiply with the tangent of 23 degree, and we can automatically obtain the slice thickness. So if you want to know more detail about how the IndoQCT can automatically measure slice thickness, you can refer this publication. Okay, this is the graphical user interface of IndoQCT for measuring the slice thickness. So we can use this one similar to the previous one. We can choose the automatic one or manual one, and after that we can just calculate button. And you can also measure in one slice, and you can also measure multi-slice. This is the example of the line automatically drawn by the IndoQCT. And this one is the profile of the line, and the IndoQCT will automatically detect the full width at half maximum and the slice thickness. Okay, and now we move to the another phantom, APM phantom. So in the APM phantom, they use the aluminum strip with the angle of 45 degree. You can see, and the APM city performance use the three aluminum strip like this, and the axial image the result like this. So we will measure the the thick of this object. Because the angle is 45 degree, so the tangent is 1. So it is only measure the thick of this object, this three object. Okay, this is the result of the axial image. Okay. And we have the three object for measuring the slice thickness. And if you want to know more detail about the technique, how to automatically measure the slice thickness, you can also refer to our publication published in the Journal of Applied Clinical Medical Physics, the automatic procedure for slice thickness verification of the computed tomography images. Okay, this is the detail of the step for automatically measure the slice thickness. So it is important to detect the object, and we can also detect the angle of the object. Okay, by using the half transformation, and after that we can draw the profile across the object, and we have the full width at half maximum, and we obtain the slice thickness. Okay, this is the result of the slice thickness for various slice thickness. This is of the profile, and this one is the full width at half maximum. Okay, and after this we will try together how to measure the slice thickness on various phantom using IndoQCT. Okay, this is the graphical user interface for measuring the slice thickness using the AAPM phantom. So for measuring the AAPM phantom, we can choose what is the object can be measured. You can choose only number 1 or number 2 or number 3 or all three objects. to measure the slice thickness by clicking this button, the star object. And in this example, we use the average, meaning that we use the three star objects. And this is using the threshold. We can use the dynamic or static one. It is recommended to use the dynamic because, as I already mentioned, there are the partial volume phenomenon, meaning that the pixel values of the star object is different if we use the different slice thickness because of the partial volume phenomenon. Okay, and now we move to the SCR phantom. So the SCR phantom using this different design. They do not use the line or aluminum plate, but they use the hole. So it is the phantom from the sagittal plane, and then the phantom there are the holes in the angle position, and then the hole will be filled with the material with material. So if we scan this module, we will have the axial image like this. So for measuring the slice thickness, it is just counting the number of the material of the object here. And the distance between the object is 0.5 millimeters. In this example, if you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10 multiplied by 0.5 millimeters. The result is 5 millimeters. It is very easy to do manual measurement of the slice thickness using SCR-CT phantom. And this is the example of the result of the image depicting the slice thickness with the different values. This one is the smaller one, and this one is the larger one, or thicker slice thickness. This is another example. This is the example if we measure the slice thickness. This one is the 2.5 millimeters. 1, 2, 3, 4, 5, because we have 5 object, and this one is the 5 millimeters because we have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this one is 7.5. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So we have the 7.5 millimeters, just counting the number of the object. Okay. And by using the IndoQCT, we can, of course, can measure the slice thickness automatically. And this is the publication, automatic slice thickness measurement on computed tomography images of American College of Radiology phantom or SCR phantom. This is the method. And the first one, we detect this material for the standard position, and then we drew the line. We have 3 lines here, the blue one and the red one. So the red one is only for the marker, and the blue one is to take the profile. So the IndoQCT will have the 2 profile from the left one and the right one. And then we will have the profile like this. And by using the IndoQCT, we can decide the threshold value, indicating with the red line here. The default is 0.4, is I not mistaken. And after that, we can measure the peak like this. So the IndoQCT will automatically count the peak of the profile, and then we will have the slice thickness. This is the graphical user interface of the IndoQCT. Okay, so the default of the threshold is the 0.35, this one, the red line. Yeah. So you can also change these values, and you can do study what is the optimum values for the deciding the threshold. So based on our experience, the 0.35 is optimum, but maybe you can do another study by using your own images. Okay, now we move to the Simon phantom. So this is the Simon phantom has the different design. They can use the one object, and another phantom use the two objects. This is the example of using one object, one plate with the located with the specific angle. And just in the IPM phantom, we can make the profile, and then we measure the full width f at half maximum, and we can automatically obtain the slice thickness. This is the Simon phantom number 1, and this one is the Simon phantom number 2. Okay, and maybe, I don't know, maybe another different type of the Simon phantom, but as I know, there are two type of the phantom for the Simon phantom. This is the for object for measuring the slice thickness. So the IndoQCT for the two object will take these two object and make the profile, and as previously detect the full width at half maximum, and we automatically obtain the slice thickness. And this is for the Philip phantom. They also use the RAM object with the different two plate at the top position and the bottom position. So the IndoQCT will detect this object automatically and through the line and make the profile as previously and measure the full width at half maximum. This one is the GE Phantom. The GE Phantom, the design is similar to the SCR Phantom. The difference is the location. The RCR Phantom, the object in the center of the Phantom, and the GE Phantom, the object in the peripheral location. There are two positions in the left and the right position. And the IndoQCT will detect, and we have this threshold and detect the max the peak upper the threshold, indicating the slice thickness. This is the design, the different design of the GE Phantom. So the GE Phantom also has the different design. In this example, the GE using the four lines for wire, for wire, two in the top and two in the bottom with the specific angles. So the IndoQCT will detect this four line and make the profile and measure the slice thickness. This is another design by the new soft phantom. The new soft phantom only use one material, one object located in the acrylic material. So it is the design of the new soft phantom. So in the QCT will detect automatically the object and through the line. So because the design is different for every phantom, so the IndoQCT has many algorithms to detect the object differently because the design is different. But after getting the profile, the process is similar, to measure the full width at half maximum. Okay, and now we move to the parameter number 2. It is distance between slices or slice spacing. Yeah. distance between slice or slice spacing, it is in the fact very important. It is as important as slice thickness, in fact. But in the reality, the parameters should be measured in the quality control only slice thickness and not distance between slice, because in fact it is very difficult to measure the slice between distance between slice. So I will show you what is the importance of the distance between slice or slice spacing. You can see here. In the z-axis, there are two parameters, slice thickness and slice spacing. So we can suppose that the accurate volume determination is not only doesn't only depend on slice thickness, but also depend on the slice spacing. So in my opinion, measurement of slice spacing is important as slice thickness. So in the previous last year, we think and how to measure the slice thickness. Yeah, it is very difficult at the beginning, and then we have the an idea how to measure the slice spacing easily using available phantoms. So this is the idea. This is only for the illustration. The lung nodule is not only affected by and we scan in another position. We will detect
Dr.
on.
We are so sorry, your voices is not here in the Zoom. Just
Okay. Can you?
Oh, ini sudah.
I think there is a
Oh, okay. Thank you.
we lost your voice several times.
Oh yeah.
Uh-uh.
Coba.
Clear?
Iya.
Okay.
Yes, it's good.
Yeah, very.
We are sorry, doctor. Your voices is lost. Okay, we are so sorry for participants. As waiting for Dr. Anam to change his microphone. Okay.
Can you hear my voice now?
Okay.
Okay.
Several participants want to if you don't mind, you go some previous slide beforehand.
Oh yeah.
Yeah,
Thank you.
since they lost your voices.
Okay. This one. Yeah.
Okay.
So we can see here the slice spacing is important as slice thickness. So even the standard quality control only it is mandatory for measuring the slice thickness. But in my opinion, the slice spacing is also very important. Okay. This is the example. The impact of slice spacing to the accuracy of the volume of the lung nodule. So we can see here, if we use the small slice spacing, then the volume accuracy is going better. Okay, we can see here. And now how to measure the slice spacing. To measure the slice spacing, we have to scan in minimum in the two locations, in this position and another one in this position. So we will have the two axial images, and then we detect the object by using the threshold. And then this one is the three object, and then by using the image processing we can decide we can eliminate the two material, so they remain only in the central position like this. So we have this one in the central position and this one in the central position of for the another slice, and then we combine these two images like this. So this is the result. This one is the slice object from this slice, and this one is the central object from this slice, and then we just measure the distance between these two objects, and we obtain the slice spacing. Okay, like this. And we can measure using this equation. Basically, it's very easy to measure. And if you want to know more about the technique, you can refer to this paper published in the Journal of Medical Physics in the 2024 maybe, or 23. 24. Yeah, this is the result. Okay, by using the IndoQCT, for measuring the slice spacing, you should have the minimum two images, and you can set here the slice. In this example, slice number 4 and slice number 5. Okay, and then you calculate, and then you will obtain this image. So the IndoQCT will measure the distance between the centroid of this object and the centroid of this object by using the previous formula, and we have these values. Actually, by using the DICOM info, we can get the position of the image. This one is the one position from the DICOM info, and this one is the position of the slice position in the slice number 2, and we can measure the slice spacing. So in this example, the set spacing should be 30 millimeters from the DICOM info. And by using this method, we get the position from the slice number 1, this position, and this one is the position from the slice number 2, and then we can measure the distance by using the previous formula, and we get the measured spacing 30.42 millimeters. So we can obtain the difference from the set and the measured slice spacing. In this example, the result, the difference is 0.42 millimeters. Okay, this is a measurement of the slice spacing using the IndoQCT. Very simple. We only decide the slice number 1 and slice number 2 for measuring the slice spacing. This is the design from the AAPM Phantom. And the question is, can we measure the slice spacing using the another Phantom? Of course. If we use the RAM material, we can measure with the same method. And if you measure using the such as the RCR Phantom or GE Phantom with the counting object, of course, you can also measure the slice spacing. So, as the previously, you should, this is the example of measuring the slice spacing using the RCR Phantom. We decide the slice number 1 and slice number 2. And yeah, because we have the many objects, so we have the profile like this. This one is the profile from slice number 1, and this one is the profile from slice number 2, and then we combine the profile, and then we detect the center of the profile from slice number 1, and we detect the central of the position from the profile number 2, and then we measure the distance. This distance is the distance between slice. Okay, and now we move to the last parameter, the slice profile quality index. This parameter is described in the book written by Professor Willy Callender in his very famous books, Computed Tomography, Principal, Design, Artifact, and Recent Advances. In this, Professor Callender, as we know, he invented the spiral CT or helical CT. So he also show the profile of the object with the different in the helical CT, as already discussed by Professor Matsubara, there is pitch factor. So if the table move faster, the pitch will be higher, and if the table move very slow, the pitch will be lower. So, and if we have the object, for example, material, solid material, and then we scan with the different pitches, so we will have the different profile. And it is already seen by Professor Willy Callender. So if we object like this, if we scan with the axial mode, we will have the relatively similar profile. But if we scan with the helical scan with different pitches, so we will have the different profile like this. So based on the Professor Callender opinion, it is important to measure not only the slice thickness but only the form of the profile, the shape of the profile. So you can see here. This is the example. If we measure the object, the same object with the different modes, with the ideal rectangle, conventional CT, and spiral CT. So by using the spiral CT, we have the same full width f hat maximum, but the shape of the profile is different. So For describing this phenomenon, Professor with the calendar introduced the new parameter SPQI, slice profile quality index. So the SPQI is the area bounded by the nominal slice width, this area, the total area, this one. Yeah, this from this one to this one, and this one, divided by the area of ideal profile, divided by this one. So if our profile is ideal, for example, so the SPQI will be 100%. But if our profile is just like the Gaussian profile, so the SPQI will be lower than 100%. So this is the SPQI, Slice Profile Quality Index. It is very nice parameters, but as we already know, this parameter is not mandatory to be measured in the standard quality control. But for the research purposes, I think it is very nice to measure this parameter. Okay, by using the IndoQCT, we can measure these parameters very easily. Just only clicking one button, and we get the profile and also the profile like this, and we will have the SPQI parameter. Okay, we come to the conclusion. The slice thickness test assures the user that the display image represents the specified thickness. And slice thickness measurements should be carried out using specific phantoms such as APM phantom, CR phantom, CAT phantom, and other phantoms. And size spacing, it is very important also to be measured. And this parameter is also affecting the volume, accuracy of the volume of interest. And by using the IndoQCT, we can measure parameters of the slice thickness, slice spacing, SPQI for different phantoms available in the market. Okay, I think this is all for me. And now we will try together to measure the slice thickness, slice spacing, and SPQI using IndoQCT. Please open your IndoQCT. And if you have any question, please write down in the chat section. Okay. I open our IndoQCT first. Okay. My IndoQCT is already open. And now I will open the example images. Now I will try to measure the slice thickness from the APM phantom. APM phantom, this one, okay. And for measuring the slice thickness, we click this tab, this one. We're using just like ladder mark. I click this button, and then we have the form like this. And in this form, we have the three sub buttons: slice thickness, SPQI, and slice spacing. This is if we using the phantom APM phantom. So this is the example of the APM phantom for measuring the slice thickness. So you can see by click the enlarge button. This is the example of image for measuring the slice thickness. Okay, and then I close this one. So I will looking for the image, this one or this one. It is better, I think, because the central object in the central position. Okay, and you can choose this one the method automatic or manual. Okay, maybe in this example we use the automatic one. Automatic one, and you can measure what is the object. You can detect the middle, top, bottom, or average. In this example, I use the average one. It is better because we have the average from three star objects. And after that, we just click this button. This is our result. And this one, it is the profile across the object, and this one is the profile, and we have the red one. The red one is depicting the full width at half maximum. Okay, you can try another parameters. For example, you choose this one, not average, but maybe you interested to only measure in the top object. For example, you can do that, top, and calculate. So the software will detect only the top object like this. Maybe there is a question. Can IndoQCT measure the slice thickness automatically if the phantom is rotated, for example? Yeah, for example, we can try together. In this example, I will rotate this image. Maybe I will rotate, you can rotate maybe 20 degree, 20 degree clockwise, like this, for example. And by using the IndoQCT, it is not uh, not affected by the rotation because the IndoQCT will implement the half transformation to detect the angle of the phantom. So if you calculate, click this button. So the IndoQCT still detect the angle accurately. It is based on the half transformation. If you want to know more deeply about the half transformation, please refer to the mathematical books, or you can refer our publication before. Okay, how the half transformation is works. Okay. This is the example of measurement using the APM phantom. We will try again with another phantom. In this example, using the SCR phantom. SCR phantom like this. So we can choose this one. So uh, we can measure the manual or automatic. For manual one, just only counting the number of the object. And you can, for example, using the zoom in, this one, and you can enlarge, and you can count the object. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe 12. Yeah, it depends. It is subjective. Yeah, it is the manual assessment. Subjective depend on the human observer. Okay. In this example, maybe I don't know. It is considered object or not. Maybe from this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know. It is considered as object or not. It is for the subjective measurement. Okay. And then we back to the standard uh, standard view. And by using the automatic method, you can, this one, no rotation method, the object reference is Boon. It is important for automatic method. Why Boon as standard? Because the Boon it has relatively high city number, so it is easy to detect. It is mentioned as the reference. Okay. And this is the threshold 0.35. This is the default one. You can change the values. And in my experience, this value is optimum one. But you can evaluate it is good or not, it is true or not. Okay. Okay, and by using this pattern, you can average meaning that we counting in the top and the bottom position. Okay, and then we just calculate this, click this button. This one. This one is the ROI. We have the two line, the two blue lines, and the red line only for the position or positioning. And then we have the two profile from right and left, and this one is our profile, and then we set the threshold with the this one red line. The values is 0.35, and then in the QCT will count the number of the object of the peak like this, and we have the result like this. The set values is 5 millimeters. It is from the DICOM info, and the thickness of the left is 5.5. The thickness now in the right position is 5.0. So the average will be 5.25 millimeters. So compared to the set standard, the difference will be 0.25 millimeters, or in percent around 10%. And APM, there are no standard for the slice thickness. Okay, this is the example of measuring the slice thickness using ACR phantom. Okay, you can also measure the slice thickness using the different phantom. For example, we use the CAT-FAN phantom. This is the design of CAT-FAN phantom. This is the example. So we can looking for the same module. I think this one. So for measuring the slice thickness in the CAT-FAN phantom, we can measure the length of this four line, this one. Okay, and in the QCT will detect automatically this four lines. Okay, we just click this button, calculate this one. So the IndoQCT will detect this one, our ROI to make the profile, and this one is the profile like this, and the IndoQCT will measure automatically the full width at half maximum and multiply with the angle of the RAM object. Okay, you can try another phantom. For example, maybe this one, the Philip phantom. This is the Philip phantom, and the slice for measuring the slice thickness, this one. Okay, so we can measure the profile of the two material. By using the IndoQCT, we can just click this button, and we have the profile like this, detect like this. Okay. And now we move to the second parameter to measure the SPQI. Okay, and the method is similar. Basically to detect the material and then make the profile and then measure the full width at half maximum. The difference, we can also calculate the area under the curve, limited by the full width f at half maximum. So I will try using the IPM phantom again, IBM Phantom, and we use the same image. Okay, we just click this button, this one. So we not only have the profile, but we have the ideal profile, and then uh, we compare the area with the actual profile divided by the ideal profile, and then we obtain the SPQI like this. This one is the values of SPQI in percent. In this example, the result is the 86.5.2%. And there is no standard for SPQI. And this parameter is not mandatory for quality control. Okay, and now we move to the example of measuring the slice spacing. Slice spacing using uh, uh, many phantoms. And now for measuring the slice spacing, we just click these steps. Okay, we have this one. We can set this one. So we should see this position. This one. Okay, this one is slice number 4. Okay, this one number 4. Okay, and this one number 5. So we should change this one slash number 4 and this one number 5. If we have many slices, you can decide what you want. For example, we have maybe 5 slices containing the object. We can set the slice as you want. Okay, because in this example we only have 2, so we have choose correctly. Okay, this is number 4 and number 5. And after choosing this limit of the slice, we just click this button. This one. And IndoQCT will detect this is for segmentation from the first slice, and this one is from the slice number 2, and this one is the combination of the center object from slice number 1 and slice number 2, and then we measure the distance. This distance of course multiply with the angle of the object tangan for the APM 45 degree. So we will obtain the slice spacing like this. Basically very easy. Yeah, very easy. Only clicking one button. Yeah. Okay. And now we will try for measuring the slice between distance between slice on the, for example, OCR phantom. So we use this one and this one. This one is slice. We can see here the slice. This one is slice number 1, and this sorry. This one is slice number 1, and then this one is slice number 2. So we change again to the slice number 1 and slice number 2, and then we just click this button, and we have the 2 profile. The blue profile is from slice number 1, and the red profile is from slice number 2. Wave profile, and then the IndoQCT will decide the center position from the slice number 1, and this one is the slice position from slice number 2, and the IndoQCT will measure the distance, and we obtain this one. This one is the measured spacing. The such spacing is the 5. It is from the DICOM info. And the result of measurement will be 5.14 millimeters. It is from measurement. So the difference is 0.14 millimeters. Okay, it is for measuring the slice spacing. Okay, I think it is all from me. You can try together. You can try by yourself first after this. And if you have any question or any suggestion, please discuss together. Okay.
Okay, thank you so much, Dr. Anam, for the lecture about the slice thickness, slice spacing, and its measurement using IndoQCT. And actually, Doctor, there are many questions, have been many questions by the participants regarding this topic. I want to read the question from Miss Afrah first. Miss Afrah asked about is there an ideal value of slice thickness for its mission suitable for a large and small object? Ini.
Yeah.
There is additional comment. Is
there an ideal?
Oh, I'm so sorry.
Sorry. This one.
Yes.
Is there an ideal value of slice thickness of each machine suitable for large and small object?
I mean, 1 millimeter, is it right to use it as ideal value? Another comment from Zul.
Yeah. If you want to obtain the image with the isotropic one, isotropic meaning that the size in the Z, X, and Y axis is similar, so you can choose the very small slice thickness. It is important. And in the radiotherapy, it is important to use the very small slice thickness because the definition of the volume will be very accurate. But if you just want to another case and you want to see image with very small noise and the spatial resolution is not the matter, so you can choose the relatively very thick slice thickness. So the choosing of slice thickness is depend on our clinical task. By using the modern scanner, we can choose for very small one to the very thicker one, very thick one. This is for the modern scanner. But if you use the old scanner, maybe the scanner only very limited option. For example, only maybe 3 millimeter and 5 millimeter. It's very limited option. But by using the modern scanner, we have the more option from very small one to the larger one. So for the choosing of the slice thickness is depend on the clinical task. Like this.
Okay. Is there still follow-up question or comments from Ms. Afrah regarding the answer by Dr. Anam? If you have any comment or follow-up question, please write in the comment. Another question, Doctor, from the YouTube, from P6QIA. Do you have an idea for measuring SPQI in ACR Phantom?
Until now, I still thinking this case. Yeah. Maybe we can detect the top of the object one by one, and then we gather together, and then we can make another profile, maybe. But now the IndoQCT cannot measure the SPQI on the SCR phantom. Maybe in the next we will find the method how to measure the SPQI using the OCR phantom. Okay, thank you.
Okay, thank you so much. Please.
Or if you have any idea, you can also share with me, and we can do the software together to measure the SPQI.
Okay, for Mr. Physics QIA, you can contact Dr. Anam at the anam@fisika.fsm.undip.ac.id if you have any idea how to measure the SQI in ACR phantom, of you can wait until we still investigate or develop this software. And another question, Doctor, from Mr. Komkom Deka from Jakarta. Thank you, Dr. Anam, for good presentation. If we change one protocol pitch from 0.6 to 0.9, the other protocol same. Their still image give good quality or worse. Change pitch less than 1, similar good image.
Yeah, thank you very much, Komkom. Yeah, very interesting question. If we change the pitch from 0.6 to 0.9, the image will be slightly worse. So the good one is 0.6. But if we choose the pitch 0.6, the dose will be higher because of the overlap of the beam in the patient. The pitch from 0.6 to 0.9, of course, the image is slightly worse. But I think the difference is not significant. I think only slightly different. Yeah, and the object, yeah, because of the phenomenon of SPQI, yeah, we have the profile. If we choose with the higher pitch, the SPQI will be wider, slightly wider, but it is not significant, I think. Yeah. Okay, so basically the image quality from 0.6 and 0.9, I think is not different significantly. I think if any different, it is very little different. But I think it is still a good image because the pitch still lower than 1. It is important to note if we use the very high pitch, for example, we use the pitch is 2 or 3, it is we should set carefully. Yeah, of course, the dose is very low, but the image is very worse, I think.
Okay, Doctor. I hope that will answer your question, Mr. Komkom. And another question from the comment from Mr. Wahyu Hutomo. Can you explain when to use rotation option in clinical case? Doesn't those phantoms always have same angle position during setup?
Thank you very much. It is only of our evolution for developing the IndoQCT. At the beginning, we detect the object and then we rotate the object at the beginning. And after that, we think that this method is not good enough. So we detect the object and its degree with its angle, and then we directly create the line to make the profile. So it is only of our evolution for developing the software, and I and our team has published this evolution in our paper. Maybe if you want to know, I will show you the paper. This one, sorry, paper. No, paper. This one and this one. Tolong dicariin nomor berapa ya? Yang di PGMPE. HMP. 103. Okay, this one. This one. Yeah, this one. This one. This is my student, Siemens. They compare the automatic one using the non-rotational and rotational method. Yeah. Okay, I will show you. And this one is the rotational method. We detect the object, this object, and then we detect the angle. After that, we rotate the object, and then we crop the object, and then we create the profile from top to the bottom. This is the first method we developed. And after that, we developed another one because we think this is not so good. So we developed the new one, this one. So we detect the center object, and then we decide the angle, and then we automatically draw the red line here, the right sorry one, this one, the red line here. So we don't rotate the object, but the line is directly perpendicular to the object, and then we have the profile. And what is the result? The result is like this. Yeah, you can see here the difference with the rotational and non-rotational method. Yeah, I think the difference is very slightly and not significantly different. Yeah, it is only for our evolution for developing the software. Okay.
Okay. How about Mr. Wahyu? Have you good enough with the answer? If you have any comment, you can write in the chat Zoom. And another question, Mr. Doctor, from YouTube, from P6QIA. Have you ever tried to find out the effect of pitch and misalignment from small degree of phantom position with this parameter measurement?
Yeah, we have done a study on effect of the non-alignment object. I will show you. I think with the different rotation. Yeah, with the different rotation. We will show you the paper describing that and published in the GSCMP, I think, like this. This one. This one. This one. You can download this paper published in the Journal of Applied Clinical Medical Physics. This is the open access paper. This is the method. I already mentioned these steps. And we measure the slice thickness with the different slice thickness. This one and this one with the different position. With the different position, we can see here of the A in the center position, and then move to the up position, and then move to the down position, and we then measure again. Is the automatic method still accurate or not?
Okay. I'm so sorry, Doctor. I think the meaning of B6QIA is about the effect of pitch and misalignment to the small degree phantom.
Oh, pitch.
Pitch and alignment, misalignment.
Yeah, effect of the pitch
and misalignment.
I forget. I think I didn't do that. Yeah.
Oh yes,
yeah.
yes.
Yeah, it is. I think it is very nice if you want to do the study on the effect of the pitch to the slice thickness accuracy. Yeah.
Yes, especially with for the phantom with the small degree such as 23.
Yeah. It's very nice to do.
Okay. Thank you. Another question, Doctor, from Mr. Wahyu Hutomo want to ensure that so the default is no rotation method.
Yeah, right. Yeah.
It is true, Mr. Doctor. Mr. Wahyu. Another question, Doctor, from offline participants. Thanks for a great presentation, Mr. Based on your explanation, for example, AAPM phantom, there are three objects. If I have pediatric chest phantom various from some materials, how to determine the best object for slice thickness?
For
Slice thickness.
what
If I have pediatric chest phantom.
Oh yeah. For measuring the slice thickness, we should have the specific phantom, just like RCR, APM, Catran, Simon, and so on. So you cannot measure the slice thickness from the anthropomorphic phantom, I think.
Okay.
Yeah.
Okay. Is there still any question from participants? From YouTube or Zoom maybe? Okay. If there is no question again, I want to Dr. Anam to give a closing statement for this session before we end our morning
Okay,
session.
thank you very much for joining us here. And we have discussed about how to measure the slice thickness with the different phantom. And inshallah, after the lunch, we will discuss about how to measure the image quality directly from the patient. Okay, please join us after having lunch.
Okay, as Dr. Anna mentioned, we will close the Zoom and you can rejoin again. At the 1 p.m. and local time, we will begin the afternoon session with the discussion about the advanced image quality measurement in the patient images. And for all participants, you can break having your lunch for Indonesian, and for abroad participant, you can take a rest about the 1 hour before we continue our summer course with the another topic with Dr. Anam. Okay, see you again at the 1 p.m. Wassalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody.
Waalaikumsalam warahmatullahi